Cardinality asks how many elements a set has, even when ordinary counting has given up and gone home. For infinite sets, size is not determined by containment, density, or how emotionally large the set looks. Two sets have the same cardinality when there is a bijection between them. We write the cardinality of A as vertical bars A, and the equation says that every element can be paired with exactly one element of B. An injection from A to B proves that A has cardinality no larger than B. A bijection is simultaneously injective and surjective, so nothing is duplicated and nothing is missed. A set is finite if it is in bijection with 0 through n-1 for some natural number n. The empty set corresponds to n equal to 0. Even 0 gets a job here. Countably infinite means being in bijection with the natural numbers. Countable means finite or countably infinite. Some books say at most countable for this combined notion. An uncountable set is simply a set that is not countable. The word does not mean mysterious. It means no complete natural number list exists. The natural numbers are in bijection with the positive natural numbers by sending n to n+1. Therefore an infinite set can have the same cardinality as a proper subset of itself. For finite sets this is impossible. Infinity has started breaking the furniture, but it is doing so consistently. The integers look larger because they extend in two directions. But a list can alternate between positive and negative entries. This displayed formula turns that alternating list into an explicit bijection from the natural numbers to the integers. Hence the integers and natural numbers have the same cardinality, called Aleph-0. A pair of natural numbers is a lattice point in the first quadrant. Reading the points diagonal by diagonal produces one infinite list containing every pair. So the Cartesian product of the natural numbers with itself is still countably infinite. Every rational number is represented by an integer numerator and a positive integer denominator. The pairs form a countable set because the integers and natural numbers are countable. Different pairs may represent the same rational number, as 1/2, 2/4, and 3/6 insist on demonstrating. Removing duplicate appearances leaves a list of all rationals. So the rationals are at most countable. They contain a copy of the natural numbers. So they are not finite. Therefore the rationals are countably infinite. Between any two distinct real numbers lie infinitely many rationals. Yet the rationals are still countable. Density and cardinality measure different things. Mathematics occasionally reuses the word large just to keep everyone alert. Now we prove the central claim. Every infinite set has cardinality at least Aleph-0. We work in the usual ZFC foundations, where the required sequence of choices is available. Choose one element A0 from A. After choosing A0 through AN, their finite set cannot exhaust A, because A is infinite. Therefore another element remains, and we choose it as AN+1. Define F from the natural numbers to A by sending n to AN. The chosen elements are all distinct, so F is injective. Thus the natural numbers inject into every infinite set, proving that Aleph-0 is the smallest infinite cardinality. To test whether the real numbers are countable, suppose every number in the open interval from 0 to 1 has been listed. Write the decimal digits of the listed number n as dn0, dn1, and so on. If the list were complete, any number we describe in that interval would have to occur somewhere on it. Construct a new decimal y by changing the digit n of the number n. Choose the new digit to be 1 unless the diagonal digit is already 1, in which case choose 2. Using only digits 1 and 2 avoids the nuisance of two decimal expansions representing the same real number. The new number y differs from xn in its digit n. Therefore y differs from every entry on the list, even though y lies between 0 and 1. The assumed complete list was not complete. Hence the interval from 0 to 1 is uncountable. Since that interval is contained in the real numbers are uncountable as well. Cardinality compares sets through bijections and injections, not through visual intuition. The natural numbers, integers, pairs of natural numbers, and rational numbers are all countably infinite. Every infinite set contains a countably infinite collection of distinct elements. So all F0 is the smallest infinity. The real numbers are uncountable, as Cantor's diagonal argument proves. Finite, countably infinite, and uncountable are now different categories rather than three increasingly dramatic adjectives.